Alright, I'm glad you all made it back. This is where we're going to start really getting interesting here. So just a bit of a recap. Last video we talked about going from this realm of pure mathematics into what we call the boundary integral equation, which this right here, in case I didn't make that clear, is the boundary integral equation. What it says is that if we want to figure out the velocity potential at any point in the flow, all we need to know is the distribution of source and doublet strengths across the bounding surface, so typically the aircraft or the body that we're looking at that is immersed in the flow. And if we know those, we can sum up these influences and we have our velocity potential. Pretty sweet, right? Well, today we're going to talk about how do we use this equation practically, because as it's written, it's much simpler and much more applied than where we were at with Green's third identity, but it's still not quite usable. Now the main issue with this is that it's a exact continuous integral. Now if we knew the distribution of sigma and mu exactly across the surface that we're dealing with, then that would be fine. We could approximate this integral to whatever precision we like, and we'd be okay. The thing is that we don't know what sigma and mu are, and we don't know for any given configuration whether there's an analytic solution for this unknown sigma and mu. Now there are some special cases for which we can know sigma and mu exactly, kind of basic canonical ones like a flow about axisymmetric bodies, that kind of thing. And those are great and all, but it's not terribly practical to use those for aircraft design, because we want to look at more than just an axisymmetric body. So how do we use this practically? Well, what we can do is we can break up this integral. So I'm going to attempt at a drawing here. If I've got some configuration over which I want to model airflow, and let's go with just a simple wing fuselage combination. So if I've got a wing, okay. If I've got a wing coming out of my fuselage, and I've got a fuselage that looks kind of like that, and we'll imagine there's a wing on the other side. That's a really terrible drawing, but that's okay. So the surface that we're dealing with is the surface of this configuration here. What we can do is we can break up the surface into chunks, and we call those chunks panels, which is where we get the name panel methods from. And so now imagine I do this over the entire surface of this configuration, and I'm going to call each one of these chunks, I'm going to call it ds sub I. So the ith chunk, or no, I apologize, I want to call this ds, so I don't want to get it confused with our variable of integration. I'm just going to call it s sub I. So each one of these I'm going to call s sub I, and I've got the ith chunk of the surface. And then let's take this integral equation that we have and let's break it up and apply it over each one of these chunks. So I can say that my velocity potential at any point in the flow is equal to 1 over 4 pi times the sum over all these I panels, and so I've got n panels. And then all I'm going to do is take the surface integral over now s sub I. Okay? And everything else is the same. So we've still got our sigma term minus mu, and let me put brackets around this, mu partial n 1 over r now it's ds sub I, our differential element of our ith panel, and that's all it is. Now just real quick to remind you, in case you're getting confused, this here again is the velocity potential due to a point doublet, and this is the velocity potential due to a point source. I'm carrying these around like this just because it's easier to express them that way. I could write this doublet potential using the formula that we've talked about in class, but I like to keep it in this form, one because it's easier to write, and two because it I think it shows the connection to everything else that's going on a little better. Okay, so this is now a little better. We've got a whole bunch of chunks, and we've defined that we're taking the integral over each one of these chunks. What we're also going to do is define that we have some analytic distribution of source and doublet strength over each chunk. So now I've got sigma I and mu I. And we can make this really any kind of distribution that we want. This is one of those knobs that you have to turn when you're developing a panel method. You can, for instance, if you want, say we've got, and I'm going to go, I drew square panels before, but I'm going to go with triangular panels. If I've got some panel here, and I want it to have a constant distribution of either doublet or source strength, I'll talk about doublet strength here first, then you can imagine that the doublet strength across this looks something like that. Imagine those are all constant. And so we have mu sub I is equal to some constant c. Now we could also, if you'd like, have a panel where we've got a linear distribution of doublet strength. So say over here it's that much, and over here it's that much, and over here it's down here. And we can linearly interpolate between those three values, and we get the variation in doublet strength across the surface. So now we've got mu sub I is equal to some average term plus mu sub x times whatever our x location is in the panel plus mu sub y times whatever our y location is in the panel. Okay? And again, this is entirely up to us. The reason we do that is because you know, if we were just want to integrate, do the surface integral of 1 over r over one of these panels, that's easy, we can do that. And if you wanted to do the surface integral of this partial n 1 over r over the surface panel, that's easy, we can do that. We have to, the tricky thing is when we get these sigmas and these mu's in here, we have to know their formula distribution so that we can integrate these, so we can evaluate these integrals analytically. Now in doing so, we're introducing some approximation. You can imagine that in the exact solution to this boundary integral equation up here, sigma and mu are going to have some, you know, they could be anything. It's some arbitrary distribution of source and doublet strength, and it's continuous. You know, it's continuous, it's well defined, it's going to be smooth. What we're doing here is if we're saying I want sigma or mu sub I to be some constant, or I want mu sub I to be some linear distribution, we've introduced discontinuities. And we have to do that because we can't solve it exactly. We have to do this discretization, and we're going to approximate mu and sigma with these analytic distributions that we have. Now, how good do we need to approximate it? Well, that's a question of you know, the kind of results that you want to get and the type of configuration that you're modeling. If we were to, let's just do a two-dimensional slice of part of this configuration, and if I've gone ahead and discretized the surface and applied a constant distribution of mu, and this is some arbitrary spatial coordinate, then imagine the exact solution has mu doing something like that. Well, if I've discretized it, and I'm saying, okay, I want constant strength panels, then maybe my discretized solution is going to look something like that. Or, if I up my mesh density, I could get a solution that looks something like that. And as we increase the number of panels, we'll get closer and closer to the exact solution. Now, you don't want to arbitrarily increase the number of panels you got, because the more panels you have, the longer it's going to take to solve this. And so we can, rather than upping the number of panels, instead maybe we want to just up the order of our distributions. So let's say we've got mu again, and again our analytic or our exact solution for mu does something like that. Then if we've got a linear distribution and it's a fairly large mesh density, then it might do something like that. And you can see already with a fairly coarse mesh, we're much closer to the analytic solution than we were with these constant strength panels. So this is something, again, this is a knob that we have to turn when we're developing panel methods. We can look at, what's the solution or what's the configuration that we're modeling, what kind of solution we're going for, what kind of accuracy do we want in the solution we're going for. If we're looking for just a rough estimate of things, then we can get away with a lot more. And so these are all things to consider when we're developing and, say, do we choose constant strength doublet panels? Do we choose constant strength fourth panels? Or do we go with some higher order distributions? Now for your project, you'll be dealing only with constant strength panels. You'll be dealing with constant doublets and constant sources, which introduces a small inconsistency that I'll describe in a later video, but we don't have to worry about that for now. Whoops. So that's really it as far as the boundary integral equation goes, at least for this project. All we're doing is we're taking this exact equation, because we don't know sigma and mu exactly, nor do we know them at all beforehand, and we'll get into how we solve for that in a later video. But we're taking it and we're breaking it up, we're discretizing it, and then approximating sigma and mu across each one of these discrete panels that we have. And again, we have different knobs to turn, saying, well, do we want constant distributions? Do we want linear distributions? We can pick it however we like. Let me touch on one more thing. If our configuration is a lifting configuration, so like the one we were looking at before, where we've got some wing and we've got our fuselage, then if it's generating lift, if we're at some angle of attack, then we're going to be shedding vorticity off of the trailing edge of this wing. And this is exactly like what we talk about when we're doing lifting line theory. You've got that shed vertical wake, and it's varying with strength along its length. Now the way that these have to be accounted for explicitly in panel methods. The way that we do that is by discretizing the wake as well. We can just break this wake into chunks of panels like that. And if this wake is straight, if it's not, changing in this streamwise direction, then it can just be one long panel. It doesn't matter, but I'll show it here with panels broken up like that, just so you can see what's going on. And then we'll apply this boundary integral equation across the combined surface of the configuration and the wake surface. Because if you'll remember, like we said, doublet panels induce a jump in velocity potential. And so when we've put in these panels here, we've introduced a jump in the velocity potential across that wake surface. And so it's a discontinuity, and we have to actually split the fluid region on the wake surface. So now the wake surface is a boundary. We have the region that we're interested in on both sides of that boundary. Unlike on the configuration, on one side we have the region of interest, and on the other side we've got that fictitious inner potential. On the wake, we have what we want to look at on both sides. So what we do is we rewrite the boundary integral equation and include now this wake surface. And it'll look like this. Phi at point P is equal to 1 over 4 pi. Again, I'm going to do the sum over all of my panels. Double integral over S sub I. Where we've got our chosen distributions of sigma and mu, partial n, 1 over r dsi. And now we include just another set of terms to model the influence of the wake, which looks like minus sum from I to n sub w. So now we're summing over the number of wake panels that we have of mu sub I partial n 1 over r ds sub w I. Now you're probably thinking, wait a second, why didn't you include source terms in there? You've only got doublet terms. Well, let's think about what sources do. Sources represent a jump in velocity potential, or sorry, a jump in the normal derivative of velocity potential from one side of a panel to another. So if we've got a panel like this, then, and it's got some source strength sigma, then we've got partial phi partial n on one side and partial phi partial n on the other side, and sigma represents the jump between the two of those. Now, what is partial phi partial n? It's the normal derivative of the velocity potential, with which derivatives of the velocity potential give us velocity. So partial phi partial n is the normal component of velocity on this panel. So this is partial phi partial n is equal to that, and this partial phi partial n, maybe it looks something like that. Okay. Now if there's a jump in this partial phi partial n term, then we've got a discontinuity in normal velocity. Now think about a wake. Wakes are free, they flow with the flow, they're convected along, and they're not supporting any loads. And so a wake can't actually support a discontinuity in normal velocity. And what we can actually say is that, if a wake, if these are our streamlines coming aft of the configuration, then our wake has to follow exactly those streamlines. And so anywhere on the wake, the velocity is tangent to the wake. And so we have the condition that v dotted with the normal vector of the wake is identically 0. And so if v dotted with n on the wake is 0, well, v dot n is just this partial phi partial n. And that's true on both sides. So we have identically that both of these equal 0. See how that works? So, again, when I write this equation up here, I'm not sure why my screen is blacking out like that, but when I write this equation up here, I can just get rid of that source term in the wake, because I know, from what I know of the flow, that on the wake, the source term is identically 0. I'm never going to have source strength on my wake, and so I can just get rid of it entirely. Now for the panel method project, we're not going to really get into wake modeling, but I wanted to touch on this because this is important if you ever do want to add wake modeling to your panel method, which I think would be a fun idea for the final project in this class. Anyway, we'll go ahead and stop there, and I'll look forward to seeing you in the next video.